All right, section 13.7, what you have been waiting for so long. We're going to find extrema of functions and several variables. Maximum and minimums, right? That's what we're going to be doing. We're going to be finding maximum and minimum locations, in particular local max, local minimums, relative maximums, relative minimums, and then in multiple variables. Okay, so definition 7.1, first of all, is going to look a lot like something you've seen before, of course. So we call f of AB a local maximum of f if there is, this is the part where it's going to look a little bit different, an open disk R centered at AB for which f of AB is greater than or equal to f of xy for all points xy in our interval R. I'll write the local minimum one in a minute, but let's just talk through what this is saying. So in two dimensions, what we do when we talk about something being a local maximum is we say there's an open interval, and inside of that interval, it's the largest point in that interval. It's the highest point on the graph. Right? That's what we say. Well, in three dimensions, we can't talk about an interval because we're looking at inputs being a two-dimensional space, right? When we're doing functions of, say, three variables, right, like what we're doing now, or having two inputs. So what we have to do is we have to talk about an open disk. Well, what is an open disk? Well, imagine a circle where the boundary doesn't count, right? That's your image. It's a three-dimensional image of what we would do to take an open interval. Because an open interval simply means an interval where you don't include the endpoints, right? So an open disk is like a circle where you don't include the boundary on of the circle itself. So it's just the interior of a circle. And what this is saying is that in that small interior of the circle, so like if you went to a mountain range, if you will, like Brandon was talking about earlier, and you sort of drew a circular region, everywhere in that big old circular region, there's the location somewhere in that region where it is at its peak, its maximum value in that circular region, in that disk. Does that make sense? Okay. The same thing's going to happen. I mean, I'm going to write down almost identical definition here for local minimum. So we call f of AB a local minimum of f if on the open disk, I'll abbreviate it a little bit. So all the details from above, but on the open disk, f of AB is smaller than or equal to all f of xy for the points xy in our disk R. And then in either case, f of AB in these cases is called a local what? Do you remember? Extrema. Yep. And I think I'll go in the order your book uses. I'd like to go a little bit out of order, but I don't want to confuse the terminology they're setting up along the way. All right, so we have these local extreme values. Think with me. What did we do in 2 dimensions to find local extrema? Do you remember? We took derivatives and we set them equal to 0. Do you remember what we called the places where the derivatives were equal to 0? Before we established if they were actually one of these points, we had a name for them. No, inflection has to do with concavity. We called them critical points. Yeah. So that's our next definition, is about critical points. So the point AB is a critical point of f of xy if AB, first of all, is in the domain. That's important. Of f, and we have 2 possibilities. Either, okay, so here's possibility number 1. The partial with respect to x equals the partial with respect to y equals 0. That's the equivalent that you've seen before, right? So derivatives equaling 0. Okay, and this is at the point AB specifically, not just everywhere, but at the point AB. Or number 2, 1 or both of the partials do not exist at AB. So in particular, we might have things where denominators equal 0 or something like that, potentially on that case. As you're well aware, most of the time we're dealing with case number 1. Those are the ones we see most examples written about, but occasionally number 2 does crop up. All right, now we're going to take this idea of critical points and the idea of extrema, and we're going to relate them with a theorem. Theorem 7.1 says the following: if f of x, y has a local extrema, at AB, then AB must be a critical point of f. Notice the direction of this if-then statement. This does not say if you have a critical point, then it is a max or a min, right? It says if you have a max or a min, it came from a point that was a critical point to start with. So in other words, these critical points, just like in Calc 1, these critical points are a good starting place. Once I find my critical points, I know these are the only possible places where I could have maxes or mins, and yet I still may not have a max or a min there. Okay? That's the way that works. Now, there's one other thing that could happen that has a name anyway at one of these particular critical points. And this is going to be definition 7.3. And you've heard me talk about this before. In fact, I've shown you a diagram of this before too. So the point P of A, B, and then F of AB, so the ordered triple in other words, is a saddle point. Do you remember me hearing that word before? Saddle point? I talked about something looking like a saddle, so your image in your mind should be like a horse saddle. So this is a saddle point of z equals f of x, y. If AB is a critical point Okay, so we've got that. We've got a critical point of F. And if every open disk centered at AB contains points x, y in the domain of F for which f of x, y is less than f of AB and points in the domain where f of x, y is greater than f of a, b. So in particular, this is the third possible thing that can happen at a critical point. We could have a saddle. So before, when we had that open disk and we were talking about the extreme points, that open disk had a place in there, potentially, where it was the highest value, sort of in a z direction, or a lowest value. It was a peak or a valley, right? Well, this is a location where if you go in some directions, it's the highest point, and if you go in other directions, it's the lowest point. And if you can imagine a saddle is exactly like that. A saddle curves upwards in one direction, like this, right, like a parabola, and then on the other side, it curves downwards, right? Can you picture sitting a saddle on a horse? That's exactly what it does. The saddle that goes over the horse's back in one direction curves downward, and the saddle that goes, it goes over the horse's back, the other direction curves upward where you sit. So this is why we end up calling this a saddle point. Okay, everybody good with those descriptions so far? All right, I think I have time to write down the last theorem, and then we'll be able to start with examples next time. All right, Theorem 7.2, which is the crux of this whole section. This is the second derivative test. Do you remember the second derivative test before? It will actually be helpful for us, I think, if we pause for a second and talk about that. Do you remember the second derivative test in Calc 1? What did it talk about?
Wasn't it like if you take the second derivative, all the zeros and then
That's part. So if you take the second derivative can actually tell you about whether the graph is a max or a minimum. So one of the ways of finding maxes and mins when we did it is the first derivative test. The first derivative test is the one where you identify your critical point, and then you do a number line, and you say, oh, look, it's increasing in this part, it's decreasing in this part, so the graph must be a maximum here or a minimum here. Well, the second derivative test is actually the one that we don't focus on as strongly, usually in Calc 1, but it's actually the one that's easier to use. It says if you take the second derivative and you evaluate the critical point at that second derivative, and it's positive, then it's concave up, which means you have a minimum. And if it's negative, it's concave down, which means you have a maximum. Do you remember that one? We're going to have a variation of that. This is our second derivative test in multivariables now. And we don't even have a first derivative test. Notice that right now. There isn't a first derivative test I'm about to show you. This is the test, okay? And it has some of that feature, that feel to it, too, about that opening up, opening downward business. All right, so suppose that f of x, y has continuous second order partial derivatives. In some open disk containing the point AB. And f sub x at AB equals f sub y at AB equals 0. So we're dealing with a critical point. That's what this is saying. We're going to define something. Who's had linear algebra? Okay, most of you have. We're going to define something called, and you may have seen this in another course too, define the discriminant. D for AB by, your book doesn't actually draw the picture, but I will for those of you who've had linear algebra. The picture is this. So your second partial with respect to x is in the top left, the second partial with respect to y is in the bottom right, and then the other diagonal is f sub xy's. So in reality, what you're going to do is you're going to take f sub x, you're going to square, f sub x times f sub yy, and then minus f sub xy squared. And this is all evaluated at AB. I'm leaving that notation out on each of the pieces, but evaluating these at AB. If you don't understand the notation with the picture in the middle, just ignore it. It's not necessary, but it does have a relationship to what we've seen there before. All right, so here's the kicker. One of four things can happen. All right, so if the discriminant value is positive and the second partial with respect to x is positive, then f has a local minimum, minimum at AB. Okay, so f sub x being positive, f sub xx being positive, is that equivalent to sort of opening upward, like a concave, that sort of picture? So you see the minimum when I make a parabola shape with my hand, right? And we could also have the discriminant being positive and f sub xx being negative. And if we did, then f has, what do you suppose? A local max at AB. Okay? So again, the picture looks like this now. It's an upside down kind of a parabola picture in your mind. Right? Second derivative means concave down. So we've got a maximum. Option number 3. And this one's probably the best one when it happens because you don't have to test anything else. If the discriminant is negative, then f has a saddle point. Think about what has to happen for x to be, or for the discriminant to be negative. Look back up at the formula up there that we've got written down. It means that those second partials with x and y have to be smaller than the second partial where the x and the y are different, or where it's f sub xy, where the partial is not respect to the same variable each time. Last one. This one's also very nice. Number 4. If the discriminant equals 0, because that's the only point we haven't done, right? No conclusion can be drawn. Now, this happens occasionally in the second derivative test with, with like in Calc 1 as well. If the second derivative is simply 0, it doesn't mean you don't have anything there. It just means that this test doesn't work. we have to do something different. Okay? That's a lot of writing on one screen, isn't it? All right. So we're going to apply this theorem next time. And it feels like it's kind of bulky, but it actually works very cleanly when you get right down to it. There are some caveats to it, though, that I want to make you aware of, and we'll see those as we do examples.